Attempting to rinse a greasy pan with cold water alone fails because the water slides right off. The grease stays locked to the surface. The problem is one of molecular compatibility. Water molecules are polar, meaning they carry a slight electrical charge. Oil and grease are nonpolar. Because they lack a shared electrical baseline, they are immiscible and actively repel one another. Forcing these two materials to mix requires a chemical bridge, a molecule capable of binding to oil on one side and water on the other. This diagram shows the resulting structure, the micelle. It is a spherical trap that surrounds the oil particle and allows it to be suspended in the water. Hand washing involves the deployment of billions of these engineered molecular machines. While physical scrubbing provides the mechanical energy required to break the grease into smaller droplets, these molecules are what actually capture those droplets and prevent them from reattaching to your skin. Building these microscopic traps requires a precise sequence of chemical reactions, starting with raw organic materials. As detailed in this chart, the properties of the final product depend on the starting ingredients. Reacting sodium salts with animal fats or coconut oil yields a hard soap, while potassium salts mixed with linseed or castor oil create a soft, easily soluble soap. Look at the laboratory setup on the right. Controlled heat applied to the reaction flask triggers saponification. Moving to the chemical equation, the strong base, sodium hydroxide, cleaves the triglycerides ester bonds. The resulting products are glycerin and a fatty acid salt, soap. Scaling this to an industrial level, this flowchart maps the conversion. The raw fat undergoes the saponification reaction, yielding a bulk supply of green crude soap. We have successfully synthesized the molecular salt. However, this crude base contains unreacted lye and is too caustic for use on human skin. Step 3 of this manufacturing document outlines the purification phase. We neutralize any remaining sodium hydroxide by adding a weak acid, like citric acid, bringing the pH down to a safe level. With a neutral base established, manufacturers mix in builders to stabilize the formula, along with preservatives and colors, before pressing it into a commercial bar. The macrostructure of the bar is complete, but the mechanical work happens much further down, at the scale of a single molecule. Looking at this isolated soap molecule on the right, we see its dual anatomy. It has a long hydrocarbon tail that repels water and a short ionic head that attracts it. These conflicting halves allow the molecule to anchor itself in water, while simultaneously hunting down and binding to nonpolar oils. This beaker diagram illustrates the initial deployment. As soap dissolves, the molecules drift through the water and encounter submerged grease particles. The hydrophobic tails immediately flee the water environment, driving themselves into the nonpolar oil particle. Next comes the anchoring phase. As shown in this detailed cross-section, the hydrophilic ionic heads remain securely attached to the surrounding water molecules. When enough molecules surround the grease, they form a closed three-dimensional sphere. This marks the completion of the micelle. The collective lift of all those water-loving heads allows the grease particle to be pulled off the surface it was once stuck to. The immiscibility problem is solved. The grease is now isolated inside a water-soluble cage, suspended in the fluid, and ready to be rinsed down the drain. But this perfectly engineered trap is highly vulnerable to a very common and disruptive environmental variable: hard water. Hard water contains high levels of dissolved calcium and magnesium ions. As this equation shows, those ions hijack the soap molecules, binding to their ionic heads and forming a solid, useless precipitate known as soap scum. To prevent this, chemists introduce countermeasures. According to this slide, compounds called builders, like sodium trimetaphosphate, are added to react with the calcium and magnesium, locking them away from the soap molecules. An effective cleaning product must defend its own chemical structure against the water it operates in, while simultaneously attacking the grease. We started with animal fats and harsh alkaline lyes, using targeted heat to cleave their bonds. This resulted in a neutral, engineered molecule with a distinct dual identity. This complex chemistry is ultimately packaged into the colorful bars sitting next to our bathroom sinks. The next time you pick up a bar of soap, check the ingredient label. You will see the base oils, the neutralizers, and the chemical builders designed to protect the formula from your chap water. Commanding these customized chemical structures allows for a flawless microscopic extraction, carrying the grease away with the final rinse.